Welcome everyone to tonight's webinar on the Common Core Algebra and Functions using Sketchpad. And I am Karen Greenhouse, and I'll be standing by quietly answering questions on the side. And our presenter for this evening is Andres Marty, and I'm going to turn things over to Andres.
Good evening. My name is Andres Marty, and I work here at Key Curriculum Press. I have for a while. Before that, I was a high school math teacher, and I had the opportunity to use Sketchpad extensively in the many years that I taught at high school. Right now I just got a little eye candy up, and you should all be able to see this rainbow screen that's made using parametric coloring, but that's actually not what I'm talking about today, although the sketch that I'm using today will be included for your download at the end of the webinar. When you get the webinar email, it will tell you about the recording and where you can get the sketch. So there's me, Andres Marty, and this is about the Common Core. We've been starting for a few months now. The fourth Tuesday of each month, we focus specifically on the Common Core, and today's presentation is about algebra and functions with Sketchpad. And I'd like to start by doing a couple of quick polls to get a sense for who you all are. So first question, what grade level do you teach? And if you're an administrator at any of those grade levels, you can mark that. I got about 2/3 of you. I'm going to leave this open for another 5 seconds or so. If you could just quickly choose one of those, and we'll see who we are. Almost at 90%. Someone's telling me I got a lot of, the icons. Thank you for mentioning that, Diana, because, yeah, I'm going to get rid of those. Good idea. All right, let's close the poll. And so we got a little over half of you are high school, but we got a good portion of middle school people. And interestingly, a significant college group, too. No administrators, which is interesting since that's part of our target audience for these webinars about the Common Core, as administrators need to learn as much as the rest of us do. And virtually no elementary people. So, second question. If you could just answer, are you in a Common Core state? Yes or no? Or maybe you're not in the United States at all. All right, we're almost up to 90%, and I'll give you 3 more seconds to close this poll. We're at 90, so let's see. So the vast majority of you are, small number of you are not, and an even smaller number are not in the U.S., and 10% don't know. Really interesting. Kind of curious. Maybe some of you don't know people could write in the chat panel what state you're from. And I'm going to ask one last question, and then we'll get going. All right, how many of you have used the Sketchpad Learning Center? So here you got 3 answers possible, because if you have no idea what I'm talking about, then that would be, what is that? And we're all about up to 80%. Be curious to get a few more people participating in this poll before I close it. Get a sense for how many of you are using the Learning Center versus not. I see a couple of you are in private schools. Yeah, the private school, if you're in a private school, then the Common Core, as far as I understand, doesn't necessarily affect you, since private schools can do what they want. All right, let's do, we're at 84%. And I'm going to go ahead and close it. And so, so interesting. We've got a pretty even breakdown here. 40% of you, yes, 30% no, and then an equally large group doesn't know what I'm talking about. So, all right. So, where to start? I'm going to start by telling you that everything I'm doing today, most everything I'm doing today is going to be activities that come from one of 2 sources. And for those of you who have never seen the Learning Center before, when you first open up Sketchpad and you get this blank sketch or whatever, you should go to the Help menu and open up the Learning Center. It's an amazing set of resources that we've developed to help people get started and develop their skills in Sketchpad, and it comes with Sketchpad. I probably should say even more generally that if you have not downloaded Sketchpad 5, which is what I'm going to be talking about, at this point we've been working on Sketchpad 5 materials for the last 2-3 years. Not to mention that Sketchpad 5 is the first release of a new version of Sketchpad in almost a decade. So it's time to upgrade, and you can download it for free if you have not already done so. You don't need to do that necessarily right now. But if you go to keypress.com and you go to the software and you go to Sketchpad, you will find the download page, and you can download the software for free. So just do it. Download it. You can have it. You will not be able to save or print, and you will be timed out after 20 minutes without purchasing the license. But you can really get a good sense for what Sketchpad 5 has to offer just by downloading it and playing with it. And when you do download and play with it, again, the first thing you should do is go to the Help menu and go to the Learning Center, and you'll find a lot of resources, video resources, and so forth. I'm going to be doing a couple of things today. There's a couple of activities where I'm going to be starting from scratch, and I'm going to be moving pretty quick because there's a lot of there's a lot to cover in the algebra and function realm throughout. I'm going to be going pretty much from middle school through high school. So things that I do that start from scratch are going to be tutorials, and these are step-by-step tutorials that you can go back and do later on your own. And when you do, these things have embedded videos and step-by-step instructions. So I'm going to go at a quick pace with the assumption that if you really want to work through it yourself, you can do that on your own time simply by looking at the tutorials in the Learning Center. The other source of activities I'm going to be going through are from the Teaching Sketchpad section. We have sample activities organized by grade level and topic. Pretty much all the sample activities I'm going to be doing today come from the Algebra section. So there's a number of these sample activities I'm going to be demoing quickly, showing you some salient points about. I'm also going to show one from higher level. And I just wanted you to know where the source of these things are. All right. So the two main points I want to get across today is, first of all, that Sketchpad is thought of as a dynamic geometry environment, because it is, but it's also a dynamic algebra environment, fundamentally, and that's what I'll be making clear by going through some of the activities. And also that Sketchpad is not only a powerful environment for exploration, but it's a powerful authoring tool to create visual models of all kinds of mathematics. And that doesn't mean you necessarily have to create the models from scratch, although it's very interesting and satisfying to do so. But we have lots of models that come with Sketchpad that you can start using right away. And those models are the sample activities I was just talking about. So again, not to be overly redundant here, but when you go to these sample activities, when I'm talking about pre-made models, I'm talking about things like tiling in a frame. That's a pre-made model. But, or mellow yellow is another one we'll go look at. So they're ready to go. And so here let's start talking standards. So I'm going to kind of break this into three parts today. I'm going to first focus on some set of standards around algebra and functions in grades 6 and 7 to start. And then I'm going to switch over to some standards in grade 8 and then go to high school. And in the middle school arena, the standards, especially in grades 6 and 7, you'll find them under the domains of expressions and equations, as well as ratios and proportional reasoning. And I'm not going to read these standards out loud. You can take a quick glance at them right now, and they will be in the sketch that you will be able to download. But the first idea I'm going to look at, this will actually be the second idea I look at, because the first thing I'm going to do is actually this tutorial, because I want to start with a from blank kind of experience, from a blank sketch. But we will then look at sort of the distributive property for rewriting expressions into equivalent expressions, and we'll also look at representing quantitative relationships. And I'm going to kind of look at the specific example they give at the end of sort of a distance is equal to rate times time. But I'm going to start with this idea of proportional relationships, deciding whether two quantities are proportional and identifying the constant of proportionality, and to represent that by equations. And so I'm going to, again, work very quickly through this tutorial number 4, which is called perimeter and area, and because this will kind of get you a sense for how you can move from sort of the geometry measurement based environment into an algebraic environment in Sketchpad. So the idea of this tutorial goes like this. Okay, I'm going to construct a circle, and I'm going to construct a line that goes through those 2 points on a circle. Whoops. And then I'm going to construct a segment that represents the diameter. And just recently I read an article about tau replacing pi. I don't know how many of you have heard of that, but this is really interesting because you could start this whole activity from scratch using the radius instead of the diameter, and then you'd end up with tau instead of pi, tau being 2 pi. But that's a little bit of an aside. So what I want to do with the circle, I'm going to go ahead and hide this dashed line, but I want to measure the circumference of the circle and measure the diameter of the circle. And I'm going to change this measurement of CB, I'm just going to change the name of it to diameter using the text tool. And now I can notice that as I drag B around, both of these values are updating. And so what I'm going to do is actually take them in this order, diameter and then circumference. I'm going to select both of these and go to number tabulate. This creates a table. And if I double click on this table, the values that I have right now will be entered into that table permanently. Then I can drag some more and do this again. And so I can do some really big circles and some really tiny circles, and I can keep adding in all of these different values. That's the nice thing about Sketchpad is you have essentially an infinite possible set of values that you can generate just by changing the size of the circle. And then what we're going to do is take this table and plot it. So I'm going to plot table data, and it's asking me what to use as my x and y. It's asking, so I'm just going to go with what's the default here, which is diameter is my x and circumference is my y. And you can see that it's plotted all these points on the graph, and this is starting to get at the idea, of a proportional relationship and deciding whether two quantities are in a proportional relationship. Well, these seem to be fit by a straight line, and they go through the origin. So it does appear to be that way. And in fact, we can take, I'm going to go ahead and use a ray instead of a line only because I'm going to keep all my values positive here. And if we measure the slope of this line, we get this interesting value, 3.14. So again, I think this is a powerful connection that honestly I don't think I made until some point in my teaching career. I don't think I ever made it as a student, that the value of pi is, I knew that I knew that circumference was equal to pi times the diameter as a formula, but this idea that if you plot the circumference against the diameter for any circle, you end up with a proportion whose slope is pi is very powerful. And I think really gets to the heart of this whole standard here. Okay? Some other things you could do after this point is try to model this with a function. I'm going to go ahead and plot a new function, and I'm going to use the value pi times x for now, and see what that looks like. Okay, now I just happen to get that function perfectly. You can see if I actually hide the line I created a minute ago, that my function plot goes to those points perfectly. And so that's the idea of of going back here, of representing it by an equation. Okay? And I know I'm going real quick. I've probably took on way too much that I wanted to get into one day, but I'm going to take a quick pause right now, Karen, if there's any questions at this point. If not, I'm going to move on.
There were no real questions. There was just show how you entered the table data, but I sort of explained it. But if you wanted to do that again real quick.
How I entered it into the table, you select the two values in the order you want them entered into the table, and you go to number, tabulate, and then every time you double click, you add a new value to the table. You can change it, double click, get another value. There's other ways to do it as well, but I'm just going to leave it at that. And remember that everything I've done so far, step by step, is explained in tutorial number 4 with embedded videos. So I don't want to spend too much time. We do lots of webinars that are about fundamental constructions in Sketchpad, and I want to really focus more on the bigger ideas of algebra and functions in this webinar. Okay, so I'm going to go to another model now. Now this is a prepared model, and this is the one about this equivalent expressions, and so at one level, this model is sort of a virtual version of algebra tiles. So, I think the example problem that they give here in the standards is 3 times 2 plus x. They give some other ones as well. But, you can model this with, x plus, or I guess 2 plus x. So let's do it in the order they do it. So 2 plus x. And then in the other way, it was 3. And then this sort of represents the length and width of this arrangement, and then you can fill in the area using individual pieces like this. And this is really just a virtual equivalent of what kids could do physically with actual algebra lab gear or any other kind of algebra tiles. And of course, instead of doing 2 plus x and 3 times 2 plus x, you could also do 3 plus x times 2 plus x and so forth, and you can see that you start to get basically a geometric model for what multiplying polynomials is. And so you have the 2 plus x times 3 plus x ends up being 6 plus 5x plus x squared. But what makes it more interesting in Sketchpad is that the tiles, unlike lab gear where they're always the same length, is here you can really have the tiles represent any variable value. So, x normally looks like this, but, x could be anything. You can make it really long or really small, and that's going to change, x squared can be less than x, depending on the value of the length of x. And similarly, you can change the values of y. So this allows for looking at these things in a dynamic way. I'm going to just show you, and it also, this particular activity, this is one of the sample activities, tiling in a frame, kind of gets kids to work, and each of these sample activities, I should also say, comes with student worksheet, teacher notes, and all that, and the sketch. So all of the directions are spelled out there. But this activity tries to get kids through a number of experiences to start to see that these regions are always formed. And again, that's something that's nice. You can add that in with Sketchpad. Otherwise, you just have to visualize that if you're a student. And that these regions define different types of pieces. That this is all going to be filled in with x squared pieces, and this is going to be filled in with x's, and so is this, and this is with ones. And then you can show the tile area that way. But in the end, the last part of it kind of allows you to get to the most dynamic part of it again, using custom tools. So now I'm going to do something where I could do like x times y, or x plus y times, let's just do x plus 2. And then, but now these things are no longer static. These values can be changed, and so it's more powerful in the sense that you see it's a truth for any value of x or y, not just what it looks like. And then you would use uh, these various tiles. Whoops, that's the wrong one. The Y horizontal. And then let's see, there's some X horizontals. And a couple of Y horizontals. And now you have a dynamic arrangement showing that x plus 2 times x plus y is equal to x squared plus 2x plus xy plus 2y. And that would be true no matter what the values of x and y. Okay, so again, I was just kind of showing a bit how a model that we provide, a dynamic Sketchpad model for really looking at the distributive property and starting at the sort of level of 6th grade, but then it continues up in through high school. And then finally, as far as the toy car, this is, by the way, I have a little color scheme here, so anything that's a red, that's the tutorial. When I mark something in red, that's a tutorial that I'm going to use to show that. If it's blue, it's a sample activity. If it's green, it's going to be a demo that I'm doing today that will be included in the sketch, but it's not something that we normally give away for free. But you'll get this today. All right, so, another nice thing here is, again, you're looking at this idea of, if you push a car at a certain speed, how far has it gone over time? But here now that was 2, but now you can change the rate here. And you'll see in this particular model, as I change the rate, the table is updating automatically. There are many ways you can do this, but in this particular model, I just really wanted to, I think it's very helpful to have an animation where you can see, okay, you just saw the 2. Now what happens if I go up to 5 and you push the car? Well, you actually see the speed of the car increase. You see the distance increase over the same period of time as the time clicks on. And you can do this for various rates. Oops. All right, I'm going to come back to this model later because, interestingly, this comes up again later. In this case, we're very much looking at it as, the distance is a function of time times the rate, which is sort of the first way you would experience rate, time, and distance in middle school. But later, when we get to some more high school stuff, we're going to look at the same situation but in a different arrangement. So just put that on the back burner. And now, before I jump into 8th grade standards, I'll take another quick pause and see if there's any dying questions, conceptual questions maybe, or anything else. Otherwise, I will go on.
No questions at this point, Andres. If anyone does have a question, make sure you're using the chat panel, but I don't see any questions, so I say you keep going.
All right, so in grade 8 is where things really start getting, it's interesting to me, really. I spent a lot of time looking at the Common Core over the last year, and there's great things about the Common Core. I mean, one thing I love about the Common Core is that I find it incredibly coherent, both at sort of the largest level and down at the smallest level. I also really like the way the ideas are coherently built up over multiple years. So when I say things are 6th grade standards, 7th grade standards, 8th grade standards, you'll find very similar types of standards up in the high school level. I'm just sort of highlighting it where it first really takes preeminence, I guess, or where it starts getting a big role. And the big thing that happens in 8th grade is that they break out functions as their own domain. In 6th and 7th, that wasn't the case. But in 8th grade is really the beginning of sort of the study of functions as functions. But you continue the strand that goes up, from 6, 7, 8 of expressions and equations. And so right now, I'll kind of go in order here a little bit more. So one thing I want to show is this idea that you can use similar triangles to explain why the slope is the same between any 2 points. So I have here, something I built today. It's fairly simple. It's just a line. You can move it around. I actually chose snap points so that right now my points A and B will always appear. They'll go from integer to integer or to lattice points. You can remove that, and it could be anything. But I was hoping to start off with just some something pretty clean, like here's something pretty clean, like, okay, let's say a fraction of, let's get 0.5, okay, so that's 1/2. And then I built a slope triangle on this thing, on this line, so E and C are on, and you can see that, you know, I can move this triangle anywhere right now. And in this triangle, I measured I built this triangle so that the one side is parallel to the y-axis and the other side is parallel to the x-axis. And, you know, I can even verify it's the right triangle by putting an angle mark here. Sketchpad will take any angle that's constructed to be a right angle and automatically mark it with a square angle bracket. And but you can kind of see right now that this triangle, you know, I mean, one way to think of it is I've measured this side, I've measured this side, and I've taken the ratio of these two sides. So the ratio of CD to DE is 0.5. And this is kind of visually apparent right now. It's kind of looks like this is 2 and this is 4. And so the idea that this side is 1/2 of this side seems to make sense. And then I can, you know, but I can change this triangle, and you'll see that you can see very clearly here that all variations of this triangle are similar. You know, this angle down here, this angle down here, it's not changing, and this angle up here is not changing. So the angles are all, and I can measure those if you want, you know, measurement evidence, which is not a proof, but it's still, for a lot of kids, you know, pretty convincing to see that the numbers actually verify that. So, you know, as I drag this around, those angles are not changing. So these triangles are just, you know, dilations of each other, bigger and smaller versions. And that no matter which 2 points I pick, this side is always going to be half the length of this side. Or you could look at it the other way and say this is twice the length of this one. And you can pick, again, some nice points again where you can see that's true. Right now it's like basically, well, it's not a nice point for some reason. But, oh, because it's measuring right now in centimeters instead of in graph paper, I mean in coordinate units. But even the more compelling, no matter what units you measure those sides in, that ratio stays constant. Now that's just for that one line. If I change the line, you know, that's going to change everything. But for that new line, if I take another line like here, you'll still see that all of the triangles that are formed by picking any 2 points on that line are similar. Okay? So I'm going to skip on to the next one. So that was this one. This is an activity that really gets into the idea of solving a simultaneous pair of simultaneous linear equations. It's another sample activity called Hikers. And in this activity, oops, I'm supposed to hide the simulation to start. Here's the original problem. It's a sort of a standard kind of problem that you would see in algebra classes. It involves rate, time, and distance. Two traveling objects, in this case 2 people. And but what's nice in Sketchpad is that you can also, you know, for a lot of kids, this is really a difficult thing to get at. And so a simulation can help here. Just for visualization purposes. So here I have a simulation where you can see what happens. You can reset it. Okay. You can try to stop it so that stops right when they get to each other, but it's kind of hard to get that perfect. But you can see that at some point they meet, 3 hours and something. One thing that's really cool in Sketchpad I end up using a lot is this idea of a time slider. So in constructing this simulation, what's really determining where Edna and Maria's positions are on that trail is time. But rather than time being a parameter, which it could be, I mean, in Sketchpad you can always just have a parameter that you could call time and give it whatever value you want. And, you know, this value is cool, and you can, with Sketchpad 5.04, by the way, for those of you who already have Sketchpad 5, if you haven't downloaded the most recent edition, like in the last few weeks, you should, because with 5.04 they built in a new thing called flickermenting. so that if I click in this parameter and I just go up, it goes, I can increase it and decrease it without even using the keyboard at all, which is really nice both for whiteboards and also for our Sketchpad Explorer app on the iPad. So that's one way of doing it, but I like having this point on a line, on an array, to be exact. So here, what is actually determining time is the position of this point on this time ray. This particular time segment, really, it only goes to 8 hours, and that's the end of it. But it's kind of interesting to be able to drag time instead of letting it just click away like it does in the real world. And it gives you kind of insights for how things are dependent on time that is different if you can isolate time as something you can actually drag. So I find this to be a powerful pedagogical tool and powerful in terms of understanding how something is dependent on time. So in this activity, again, this activity you can download and go through it yourself. I'm not going to go through the whole activity play by play. I just sort of want to get to the big salient points about it. But, Edna's going uphill 1.5 miles per hour, so, kids can figure out things like, oh, what, 1 hour she's at 1.5. Oops, that's not right. Because at 0 hours, she hasn't gone anywhere. But at 1 hour, she's gone to 1.5 miles. And then at 2 hours, she's gone 3 miles, and so on. And then, you can even have this question, why does Maria's distance start at 12? Why do they all say 12? You get to this idea that her initial position was way up here, 12 miles away from the trailhead, since we're measuring from the trailhead. But again, having something visual to point back to is pretty powerful. So she's at 12 miles. She's going 2 miles an hour. So after 1 hour, she's down at 10 miles from the trailhead. And then you can start taking these values and you can plot them. You can select them and actually select the time and each of them, and you can plot them as x, y. All of these directions that I'm saying out loud right now, they're included in the student worksheet that comes with this activity. So again, I just want to kind of get you the sense of it. I'm going to plot another point as x, y, and this point here is actually just the point that defines the scale of the graph. I'm going to hide that one for right now. And you can see that, you'll build up these points after a while. So it's really getting into well, the standard I'm addressing right now is prior to this one, but the idea that an ordered pair represents a functional relationship, and so I'm going to skip ahead to where you get to by the end. By the end, the kids will have plotted these green points from the table and these red points from the table, and you can see that they each appear to be a line. And I just realized there's a big flaw in my sequence of my presentation, because there's something I was going to come to later that it's kind of important for me to talk about before I get to the finale of this point, which comes up in tutorial 5. So I'm going to come back to this in a moment, and then we'll go through the rest of the 8th grade stuff. But right now I would like to jump to tutorial 5, unless, Karen, there are some questions that I should address first.
There was a question about how you got the slope triangle, and then there's a question about the flicking.
Flickramenting?
Yes.
The slope triangle, again, I wasn't intending to spend too much time in this particular webinar talking about constructing things, because the vast majority of our webinars do that. But, at the risk of spending too long on this, I'm going to quickly show that you can do, here's my line. I put 2 points on the line. I chose the x-intercept and this point and constructed a parallel line. I did the same thing with this point and this one. I'll construct. And then I can construct a polygon using those points, and that's what I did. And then I just used a hide show button to make it all, you know, you can select a bunch of stuff to make a hide show button, so that's why it just was gone and then it came back. The flickermenting I was just saying is a parameter value. We'll see that in a second, actually. We'll see that in tutorial 5, so let's just wait till we get there. All right, so in tutorial, and I'll get back to that flickermenting. So tutorial 5 is dynamic algebra, and it's the tutorial that introduces plotting functions and using parameters in a function, so that seems like the appropriate place to talk about flickermenting. The thing I was saying earlier is if you haven't downloaded the most recent version of Sketchpad, you should, because small changes get made all the time, little bug fixes and minor improvements, but you don't have to pay extra for this. If you already have Sketchpad 5, you can download 5.04 for free, and it will include the flickermenting capability. So let's look at tutorial 5, the concept here. And this concept, just to give it some Common Core an anchor in the Common Core, what I'm really doing here is from the high school algebra standard, understand that a graph from an equation in two variables is the set of all its solutions plotted in the coordinate plane, often forming a curve, which could be a line. That is, to me, one of the most fundamental understandings of algebra. And it's something that I think the vast majority of kids don't get, because they so quickly get to the point of thinking of a line as a picture of a function and not as a relationship of input and output values, that they get very fluent at thinking of a line without even thinking about this conceptual underpinning of what a line is. And I think this tutorial does a beautiful job of getting to the core of that understanding. And so what I'm going to do is I'm just going to create a parameter, and I'm just going to call it n, and it's just a number. And then I'm going to perform a calculation. Let's change this because 1's kind of a special number. You never know what's going to happen. So let's make it 5. And then I'm going to do a calculation using this 5. And it can be any calculation. It can be something kind of straightforward like 2 times, but instead of, I'm going to click on n here, so it's 2 times n minus 3. But you could use x squared, or you could use trigonometric functions. But assuming that we're at the middle school level right now, I'm going to do something like this. So, 2 times 5 is 10, minus 3 is 7. Well, that makes sense. It's just a calculation. And I'm going to rename the label out. And notice that I can change the in. It's a parameter, but the out is not a parameter. So you're already starting to see that there's something difference between these two things just by doing a calculation. I can't just change this. I can only change this. Now, the thing about flickermenting that we were just talking about earlier is with flickermenting, I can now take a parameter that's in a box, and I can just, if I do it right, just pull up. I just click and go up, and it starts increasing the parameter's value just by dragging up. Or if I drag down, it decreases the parameter's value. And the farther you go, the faster it goes. So it's kind of a really cool and satisfying way to change numbers that's much more interesting than just changing them by typing in another number. It's similar to using the plus and minus keys on the keyboards, which you can also do to increase and decrease values, but I love the little animation graphic that you get here too. Anyway, that's in out. What I'm going to do now is take this value, this in, this out, and I'm going to plot them as xy. And so a whole bunch of stuff just happened. In fact, I realize I've done this tutorial wrong from the get-go, but that's okay. We'll fix it in a second. Because what I really wanted to do is right now I've got one point that's controlled by this parameter. But what this tutorial really gets at, and if I had done it correctly from the get-go, which I will do now, is rather than starting with a number, you want to start with just a point that's on the x-axis. Because this is something that can be dragged around. And so what I really want to do is take this point on my x-axis and measure its abscissa, its x-coordinate. And what I'm going to do now with my calculation that I did a second ago is I'm going to double-click it, and I can edit it. So instead of using my parameter here, what I really want to do is replace it so I can just delete in this formula and now click on this x of a. So now I'm going to use my x-coordinate. When I drag my x-coordinate, and this, let me get rid of this for now. As I drag my point A around, you can see that the value here is dependent on the position of A, and that this value then affects the out value. So the parameter that I put in here originally, good for showing flickermenting, but I'm not actually using it right now, so I'm going to delete it. This one here, that is my x-coordinate of my point on the line, I'm going to call it in. And now I'm going to do what I did a minute ago and take this in value and this out value and plot them as xy on my graph. Now when I drag A, you'll see that this point moves with it. And you'll see that, its horizontal position is always identical. It's going to line up directly above or below A. And meanwhile, the vertical position is determined by whatever calculation I used. And then what I'm going to do next is take this point and trace it. Now watch what happens as I drag A. As I drag A, I get this trace, but what I love about this trace is it's not a perfect line that is just a magic thing that appears. It's actually a bunch of traces of this point as imperfect as my dragging is. If I drag, anything I do, I'm only going to get a point if I happen to move A to every position. And so I can go really slow and do that. But it's really kind of emphasizing this idea that, if I can jump all the way back to this. Oops, no, it was the high school. Here we are. It's the set of all its solutions plotted in the coordinate plane. These are all a bunch of solutions plotted in the coordinate plane, the ones that I happen to have picked by the position I've moved A towards. And so even though this standard is located in algebra, I think it's pretty much a fundamental understanding that needs to be developed in middle school for kids to really understand what a function plot is. And once they have that, at some point you are going to move ahead to a more symbolic and abstract idea of a function plot. And when we get to that point, then you can type in a function plot like 2x minus 3, which is that same line. And you can see that, that line really represents all the possible traces that I could make. I'm going to make this line a little thicker. And I'm going to go ahead and stop erasing. And I'll go ahead and erase the traces I already made. And you can see at this point stays on the line. But then you can start adding a whole, this is where things get really interesting quickly, because now I can say, okay, well this happened to be 2x minus 3. What if I had changed this? What if I created a new parameter now and I called it m and made it equal to 2? But now, instead of multiplying by the number 2, I'm going to multiply by this parameter m. And what happens now if I vary m? Well, so now you start to get to look at a whole class of lines. Here I'm increasing or decreasing the value of m, and you can see now I'm using the flickermenting to change m. You can also do this with the keyboard using plus and minus. You can also animate the parameter. And so then it'll go through a whole continuous range of continuous set of values. And this idea is really powerful. It's more generally, it gets to the idea in the high school standards of identify the effect of replacing f of x plus k or k times f of x, so forth, on a function plot. We happen to be working with a very simple function plot, just a linear function. But in any case, I think it's, and then we can change, this is just a linear function, but we could take this and then experiment with, well, what happens if this we did x to the second power, and now what effect does changing this parameter in front of m have? Well, I'm going to go up. So it's negative, and as soon as it becomes positive, it pops the other way. So you can see there's a lot of sort of dynamic motion and movement here that connect different things together. All right. So sorry for the little detour ahead. Just want to come back and bring closure to this idea that here you have the same thing going on. This is really, in some ways, a more sophisticated situation because now you're looking at two equations. You're looking at two sets of, the position of Edna and the position of Maria are both dependent on the time. And so, you can show the movable points here, and instead of just having the one point moving in its line, you can now see that each point is moving in its line. This is nicely color coordinated too. Or you can trace both movable points. And so it's just like what we looked at in tutorial 5, except it's two of them. And it gets to this idea of a solution of a system of equations, in that there is this one place, one point in time, where the two of them are at exactly the same location. They are both 5.1 miles away from the trailhead, albeit one's walking away from it and one's walking towards it at 3.4 hours. So the system of equations really is just two of the equations like what you do in tutorial 5. By the way, just to bring tutorial 5 to a full close as well, other things that you end up doing in there is cool stuff like this. You can take in this case, it's the m that is affecting what the values of things are, and here's the function, and so I can construct a family of functions, and so where I have some control over the domain, which is another piece of the Common Core. You'll notice that all mine are going up right now. The preview, they're all showing up because my domain is positive only. So let's change my domain from -3 to +3 and kind of see what that looks like. And so anyway, it created 31 members of this family of functions between -3 and +3 for m. All right. Well, I got about 10 minutes. I got way more than 10 minutes of stuff. But I'll take questions right now if there are any. I think I can probably do pretty good justice to what's left here.
I think we're doing good. And,
again, everything's available.
Get through.
Okay. So going back to the 8th grade standards now, we're going to look at sort of we looked at the simultaneous linear equations. We looked at the slope triangle. We're going to look at two things now. I describe qualitatively the functional relationship between two quantities by analyzing a graph. We'll look at mellow yellow, and then we're going to look at this idea of understanding the functions of a rule that assigns each input to exactly one output. Arguably, we've already been doing that in some of the previous activities, but we have a really great model that I'd like to present for this. So first, the mellow yellow is the situation, what does this graph tell? And you can talk about it, and then you can press go, and you'll see that you have a simultaneous, an animation or a simulation of this situation, as well as a graph. And then you would discuss, ideally, before I even press go, you'd already have a discussion of what does this graph show. And then you press go, and you see it, and eventually you have kids come up with a story, and you can see how well it matches with the given story here. There's various things. This really gets back to being able to identify various features of a graph and a function, but there are values here. We have an idea of how far away the story is on this axis. We have an idea of how long the whole trip took on this axis, and then there are various periods during the trip the horizontal part, again, that's something that kids often don't understand at first, that time keeps on moving but the distance is not changing, so it's a standstill. And there's also the relative rates of this segment versus this segment of the line, this being steeper, and it does in fact mean that mellow yellow goes faster in the simulation. And that's the first step of sort of the beginning of this, but then it goes into way more interesting things. Now you can do things, whoops, reset. Here you have a situation, and the question is, does the graph match the story? And then if it doesn't, now the kids can actually change the graph. So they can drag these points around and make the graph differently so that it does match the story. Notice that if I change the distance of the stop at the end point here, it changes the simulation, because in fact if I drag this down, the corner store is becoming closer. It's actually no longer as far from their house. And if I drag stop this way, it's just going to change how long it takes to get there. Interesting things happen though when you start dragging these points around. You'll bring this point over here and all of a sudden it all falls apart. Well, why is it that when I try to bring this point to the left of this one below it, or actually at the point where it's directly above, does it all fall apart? And that generates some interesting discussions. Is this broken? That's a great question to just sort of leave out there for a while. The answer is it's not broken. It's just impossibly two places at once. That's pretty deep understanding of what a vertical line means. And then the nice thing about this is that this animation is controlled by the graph. So whatever you end up leaving the graph, this will animate according to what you've done. So this in fact is a stretch where mellow yellow is going backwards and then forwards again. And they can also change the story if they wanted to. This is just text. If they'd rather change the text, they could do that. But I think this is a great activity in multiple representations and really building up that understanding of a functional relationship. Now, this idea of a function input-output, I think that one of the best activities we have that gets this idea out there is this Dynagraph, introducing Dynagraph activity. And I'm not, if anybody wants to venture into guessing in the chat panel what kind of function this is, I'd be curious to see what people think. So in the chat panel, what kind of function is this? You see that A is the input and its output is moving. F of A is moving with A. See parabola, I see quadratic. Now, one of the greatest things about this model is what it doesn't have. And what it doesn't have is what? What's absolutely absent from everything you're looking at right now? Numbers, exactly. There's no numbers. So this idea of a functional relationship, it's not that y equals 2x. That's, kids think of functional relationships always in terms of their numeric representation. But this has nothing to do with numbers. It's two things moving back and forth on double number lines. Double number lines, by the way, another big deal in the Common Core. So I will tell you it's not quadratic, actually. And I think I won't give it away yet because I'm going to animate B and let you think about that one for a second. So again, using the chat panel, what kind of function is what kind of function is G? All right, I see. I see linear. It is linear, but in fact, it's a very special case of linear. Some of you have already answered it correctly. It's a constant function. Whatever B is, G of B is exactly the same thing. So it's constant. I mean, if we wanted to give it a value, if B was 17, then G of B would be 17. Another thing we don't have here is 0, right? I mean, there's this hash mark in the middle, but we might make assumptions about what that is, but we don't know. Now, this one, on the other hand, I'm going to stop it for a second and drag it by hand. Notice that it looks to me like the distance from the hash mark to A is about half of the distance from the hash mark to F of A. F of A is twice as far away. And if I drag this another place, it still looks like it's twice as far away. And in fact, it's always twice as far away. So this is not an exponential function, actually. It very much is a linear function. All right, what about this one? I like frog function. That's good. I like the smiley faces. But yeah, I mean, this to me is the most vivid representation of a step function I've ever seen. I mean, it's literally taking steps, but that's exactly what it is. It's absolute value, I think. Or not absolute value, sorry. It's a round up, truncate, or round up, one of the two. And then this one, now look at those of you that thought f was linear, or quadratic, I should say. Take a look at D and see how it's really different from the red function, right? There's two big differences. One of them is that the output is always positive. And the second one, which is a little harder to notice, is that it's not moving at a constant speed. Unlike the, let me stop B and C for a second. If you look at A, you know, f of A is moving at a constant speed. It's a faster speed than A, twice as fast in fact, but it's constant. And here, with D moving, right now you can see it's moving really fast, and then it slows down, and then it goes really fast backwards. So, you know, this is, and for those of you that need to know the answers, it would be unfair if I didn't show them to you. So there they are. Okay? The next page of this activity jumps and starts showing the number lines and connects this idea of functions to the double number line, and that's all I'm going to say about that. Wow, 3 minutes. All right, what do I got left? Again, you'll get this whole sketch, so anything I don't get to, you can look at your own. But you know, we've looked at this. I'm not really going to go into this model much. I mean, there's another model that we have that you get for free, this balancing model. But what I really like about it, you know, is it really, you know, the balloons pull up. So, like, if I take away a balloon, this side gets heavier. But the idea of zeros, if I have a -5 and if I bring a +5 here and a +5 here, it all balances out. But the nice thing is if I take this -5, you know, this balloon and this weight together really balance each other out. That's a 0. I can remove it, and it doesn't affect the balance. And then, you know, that'll lead to being able to really look at equations first with the model. And again, it's a dynamic model, so it has a little bit more utility than any kind of physical equivalent. But you see that 0 moving away together, you know, and then you'll see over here another 0 moving away together, and so on. And then you can always use the Sketchpad marker tool that comes with Sketchpad 5. You know, say like, well, each of these groups is, you know, 1x is equal to 2. All right, little function slider thing here. This is sort of kind of brings this to more detail. I'm just using the example of a quadratic. But here I've just graphed a function where I have these sliders built in, and so similar to what I was showing you earlier, right, you can drag these to change the value of A to see what happens, change the value of B, see how that affects the graph, change the value of C. But the family of function thing here is really fun too, because they're each different. If I take this parabola and this, actually this point and this parabola, and I construct a family of functions, I get the family of functions we were looking at earlier, different variations of up and down, you know, with the coefficient value up here. But if I undo that and instead construct a family of functions where I use B in this parabola, a very different look, right? Now I'm getting this sort of left and right thing going on with the families, right? And and do that one too. Let me see what happens if I use C in this parabola. And here I get sort of variations of going up and down. And now I can change a different parameter and manipulate the whole family of functions. So like this whole family, you know, goes up and down as I drag A. Anyway, just really powerful stuff. The idea of using sliders to change values continuously is tactile, it's visual. It's just inherently more powerful than just symbols on a page, even diagrams on a page. Another model we have here, the unit circle. This one's great for the, here's a unit circle. You can animate point C, measure the arc angle, and measure some various things associated. And here you have a right triangle. And the right triangle has this angle, which you can change or whatever, and changes the lengths, and you can get some ratios. And so kids do a lot with right triangles in algebra and geometry, and then they get to algebra 2 or pre-calc, and they're dealing with unit circles. But this idea that they're actually related to each other, this is a powerful way of showing that. Here I'm just going to take this, put it here, and now I'm going to merge this. And so it's actually going to merge that triangle to the unit circle so that you can see all the things that were true about that right triangle are still true. It's still the same right triangle. It's just been merged into this unit circle. And now you can animate this point and see how those things are connected. So I think I've maybe done it very quickly, but I've gone through this, all of the things I meant to go. Last thing I'm going to say, and then I'll take any questions. I realize we're a couple of minutes beyond here, but like I was talking about, the narratives at the beginning of each section of the Common Core, I think, are just beautifully written. They're actually like pieces of literature where it's a coherent story that's told. And I had some fun, like at the beginning of this functions. They give a couple of examples. This one of 10,000 invested at 4.25%. And then remember I told you about the toy car that it's going to get inverted later. Here, you have usually you're always looking at distance as the output of rate times time, but here they're talking about a time function. How long does it take to drive 100 miles depends on the car's speed. The time is a function of the speed. So I won't really have a chance to talk about these, but they're included in the sketch so you can play with them yourself. Again, using a time like this, I created this. I just represented those two problems straight out of the beginning of the Common Core. But I wanted to give it sort of a geometric kind of visual, something you could look at growing instead of just numbers, instead of just lying on a plot. I actually wanted to see something physically get bigger, and so that's what this is about. And then, this is the time function here. The idea is sort of you could animate time, and you can try to, it's going 25 miles an hour. How long does it go to 100 miles? Well, I'm just going to try to do it by eye here and try to stop it, except I didn't press the button. Do I have a time slider? I do. So I can actually manipulate it back here to 100 miles. And then I could take this speed and this distance and start plotting, tabulating those like we had done earlier with the circumference and diameter. And so the speed gives me a distance of 100. Well, what if I change the speed now to 20 miles an hour and, reset and animate it? And in the interest of time, I will just use the time slider again. So, oops, I didn't want to get the speed and the distance. I wanted to get the speed and the time. Otherwise, it's always going to be 100. It's not very interesting. So delete that and actually get the right two variables. I wanted the speed and the time, and I want to tabulate those. There we go. Oh, I had done it earlier, and I had a whole bunch already done. That's what happened here. So, but you get the idea. And then you can plot this table data. And you can see that this ends up generating something very different, right? The inverse function. If I picked some really, really slow speeds, I'd get some more, much larger times, and so forth. All right. I'm sorry for going 5 minutes over. Karen, are there any questions? That's all I was planning on showing.
Not really. There's a couple questions about when all this will be available and how to access the sketches. So again, we will post a recording along with this sketch that Andres has been working through. So all of the documents that you've seen today will be part of that sketch. You do have to have Sketchpad to open it. So if you have not downloaded Sketchpad, you can do that from our site, keypress.com/GSP, and you'll get right to the download. You can, once you download it, you can actually, before you get the archive, go to the Help menu and go to the tutorials right now, and some of the sample activities are already in there. So Andres is going to quickly just show you where that is if you want to not wait till Friday, basically. But thank you all so much for joining us. I know we've gone past our time, and as usual, we always run out of time, so we probably need to make these longer or try to cover less. That's one of the things. We do have webinars coming up every Tuesday. Our next webinar is next Tuesday, and it's using Sketchpad again. And it is all about area. And this is a beginning level Sketchpad, so it's going to go a little slower and a little bit more how to do things, but it's going to be focusing on area, and that's next Tuesday. All the webinars, I noticed we had some people coming in really late, and I just want to remind you that our webinars start at 7 p.m. Eastern Time. And so if you're in Central Time, that means they start at 6. Pacific, that's at 4. So just keep that in mind. We don't change the time, so it's always 7 p.m. Eastern Time for the next time.
And yeah, when you download these sketches, I mean, if you download these activities from the Learning Center, they come with, you know, like a student worksheet, teaching notes, and the sketch itself. And I see a couple of you said, you know, less is more. I just couldn't help myself. I really wanted to get a lot of, because there's a lot of sort of big ideas that go through from middle school through high school, and I wanted to get that whole range. And there's just a lot there. So I wanted to just present various things that you could now follow up on your own, depending on where your interest level lies. So, but thanks for bearing with me as I railroaded through that whole thing.
And just a quick question, and someone was asking about areas from geometry. Yes, the webinar coming up next week is areas. It's a geometry-focused webinar. You can see the details in the description on our website. And if you're looking for specific content, don't forget we have a ton of archived webinars at our site, again, keypress.com/webinars, on many topics. We've done calculus, algebra 2, geometry, middle school, elementary. So if you're looking for something specific, check the archives out. You might be surprised you'll have some things there. So thank you so much, and we love that you are joining us, and we hope to see you in the future. Have a lovely evening.
Thank you very much.